Good evening. I'm Dick Meserve, the president of the Carnegie Institution. I'd like to welcome you to our lecture this evening. This evening's lecture is being sponsored by the Royal Norwegian Embassy, the Norwegian Academy of Science and Letters, and the Kavli Foundation, in addition to Carnegie. We will have the opportunity this evening to hear the Laureate lecture by this year's winner of the Kavli Prize in Nanoscience, Professor Mildred Dresselhaus. I'll have more to say about her in a moment, but before I introduce the speaker, let me invite the representatives of the various organizations that sponsored this evening's event to provide a few words of welcome. We'll hear first from the Norwegian ambassador, Dr. Kari Aas, who has been the ambassador to the United States for all of 10 weeks. We'll hear from the president of the Norwegian Academy of Science and Letters, Dr. Kristi Strømbull, and also from the president of the Kavli Foundation, Dr. Robert Kahn.
Thank you, Dr. Meserve. Yeah, that's right. I've been in the ambassador for 10 weeks in Washington, but I can assure you that I've been in this building many, many years before that. I was here with His Highness, the Norwegian King, back in 2005 when we celebrated our 100 years independence. So I'm a veteran in this room. I'm very new to the United States. Dr. Dresselhaus, ladies and gentlemen, it's a great pleasure for me to be here this evening. New and frontier discoveries are the result of determined work by the many women and men like you who have devoted their lives to the field of science. Dr. Mildred Dresselhaus is one of those highly devoted people who have, through a lifetime dedicated to science, done frontier research within frontier areas, achieving research results so cutting edge it might take years or even decades for us to fully understand their implications. For Norway, collaboration with top US scientists has always been important and highly valued. Within science and technology, the US is a beacon and a point of reference for other nations regarding both funding systems and the quality of research. This is certainly true within Dr. Dresselhaus's field of nanotechnology. The US sets the standard when it comes to public investments in nanotechnology. No other nation comes close. In 2010, the United States invested, I have been told, $2.1 billion. Russia was a distant second, investing less than half as much. And when it comes to results, internationally, the United States tops the list of published patents in the field. Dr. Dresselhaus, who many call the queen of carbon science, continues in the great American scientific tradition, and we gather to honor her tonight. It will be difficult to overstate the influence the United States has exerted on the field of nanoscience. It's not just a question of dollars, it's also about an investment of time. The US was one of the earliest to adopt a nanotechnology strategy. Many other nations, Norway included, have followed the Americans' lead, adopting similar strategies. Last year, at the Transatlantic Science Week in Houston, a new collaboration between American and Norwegian scientists was initiated. As a result, American and Norwegian nanoscientists are now working together in nanomedicine, petroleum application, and nanomaterials for use in the field of energy. And I'm sure we will continue to develop even more ways to collaborate in the future. The first notion of nanoscience started some time ago. Richard Feynman's speech in December 1959 at the American Physical Society is considered by many to be the starting point of nanotechnology. Dr. Feynman ended this speech by promising an award of $1,000, and I quote, "To the first guy who makes and operates an electric motor, a rotating electrical motor which can be controlled from the outside and, not continuing in the lead in wires, is only 1/64 in cube." End of quotation. This was more than half a century ago. I don't know if anyone has claimed the prize yet, but the Kavli Prize award given to Dr. Mildred Dresselhaus last year is certainly a step in the right direction. Someday, we might finally meet Dr. Feynman's challenge, or perhaps the field will take us in entirely new directions. Only time will tell. It is a privilege for me, and it's a privilege for the Norwegian Embassy to be here tonight to honor Dr. Dresselhaus, and I would once again like to extend my sincere congratulations on your award, Madam. I want to wish you all a pleasant evening, and thank you very, very much for your attention.
President Mercer, Ambassador Aas, President Kohn, dear Mildred Dresselhaus, ladies and gentlemen. This year is the 5th time the Kavli Prize Laureate Lecture is held in Carnegie Institution for Science. The Norwegian Academy of Science and Letters highly appreciate this cooperation with the Carnegie Institution for Science. The speaker today is Dr. Mildred Dresselhaus, the Kavli Prize Laureate in Nanoscience in 2012. The Kavli Prize is a partnership between the Kavli Foundation, the Norwegian Ministry of Education and Research, and the Norwegian Academy of Science and Letters. The Kavli Prize is awarded for extraordinary achievements in 3 research areas: astrophysics, nanoscience, and neuroscience. The Kavli Prize is awarded every 2 years in Oslo. The first time was in 2008. The prize is awarded by His Majesty the King of Norway. The purpose of the prize is to recognize outstanding scientific research, to honor highly creative scientists, to promote public understanding for scientists and their work, and to foster international cooperation among scientists. For each of the 3 prizes, astrophysics, nanoscience, and neuroscience, a prize committee is appointed by the Norwegian Academy of Science and Letters. Members of the committees are chosen among world-leading scientists within their field. The work done by the committees has given the Kavli Prize its high international reputation. The Kavli Prize laureate lectures have become an important part of the Kavli Prize activities. This year, there will be laureate lectures in Tokyo, Berlin, London, as well as here in Washington, D.C. Today, we are here in Carnegie Institution for Science to honor Dr. Mildred Dresselhaus. I'm very happy to see you again, Mildred Dresselhaus. You charmed everyone during the Kavli Prize Week in Oslo in September 2012, and now I look very much forward to hearing your lecture. Thank you.
Well, good evening, everyone. I'd like to begin by bringing regards from Fred Kavli. This is a photograph of Fred Kavli delivering a speech at the time of the awards ceremony in Oslo in September of 2012. And we're all here, and the Kavli Prize exists because of the vision and commitment of Fred Kavli. A little bit of history might be helpful. Fred, the partnership with Norway, as so well described, is really a result of Fred being born and raised in Norway. He was born in 1928, and he ended up immigrating after the war in the mid-1950s to the United States. And he often says he gained his roots and his values in Norway and everything else from America. He came here basically as a classic immigrant, of course, educated in Norway with a degree in engineering and physics. He was here less than 2 years before he founded a company, which 40 years later he sold for a very nice fortune. He also began investing, as many people do in the United States, in Southern California real estate. Now, when I tell you that he invested in Southern California real estate, it matters when he started. And he started in 1960. So he actually has made 2 fortunes, one by building a high technology company, and one by building essentially a real estate empire of industrial and commercial real estate in Southern California. But he had a dream, and he often tells the story of sitting in the fjords in the valley where the family farm was and where he grew up, and looking up at the sky on a clear night. Not all the nights in Norway are clear, but on a clear evening. And you know, there is no extraneous light. So the sky is just brilliant with stars. And maybe he could see the aurora as well. And so the story basically is, if I ever am lucky enough to gain the resources, I will give it back. And I will give it back to understand the universe. And that opportunity came to Fred in the year 2000. He sold his company, and with some of the resources, he founded the Kavli Foundation. The vision and the mission was actually well stated in part by the Kavli Prize. It is really to support basic science. Science that will advance our knowledge without necessarily knowing at the time whether or not it will make a difference from a practical point of view. And that is crucially important, because our core understanding about what will be important is impossible to know ahead of time. But history tells us, if you invest in science and you make the discoveries, life will be better for everyone. And we've had 150 years now of establishing that fact. The average life expectancy in the United States at the turn of the last century, in 1900, was around 50. And today, the average life expectancy in the United States is north of 80. And if you're born now, it's more like the mid-80s. That's an extraordinary change in the life expectancy of human beings, the largest change ever in the history of humanity. And you can trace it all to the quality of life we have. And when you look at the quality of life and medical care and everything else, it's underpinned by the basic discoveries in science. So that was Fred's vision. And he actually is a very practical person. And I'm proud to be president of the Kavli Foundation because the vision is something that I personally deeply believe in. We started and have a series of programs. I won't go on too long. I just want you to understand that this commitment is really to supporting science as much as to recognizing great science through the Kavli Prize. The largest program we have is actually a series of 17 institutes around the globe, 11 in the United States, 3 in Europe, and 3 in Asia, in which we aim to endow institutes with numbers in the order of $10 to $12 million each, where the income from the endowment can be used at the discretion of the scientist to advance ideas that they have for making great discoveries. Not everything works out, but that's the nature of it. In fact, it's important that you have some breakage and failure. And so he had that vision, and the institutes got established before the prizes. That's an important fact. So the prizes began in 2008, but the institutes were first founded in 2004 and 2005. And we continue. We just announced our latest institute at the University of California, Berkeley, just 2 or 3 weeks ago. So I would close by saying Fred Kavli is in the tradition of this great institution. And one of the great strengths that goes somewhat unstated in the United States is that one of our greatest assets is philanthropy. It is a tradition of giving back. It is a tradition of recycling wealth. From the time that Andrew Carnegie said, if you die with your wealth, you die poor, to the Gates-Buffett pledge that you should give away at least half your wealth 110 years later. So Fred is in that tradition. And we're just extraordinarily proud to support science and extraordinarily proud of the winners of the Kavli Prize, particularly Professor Mildred Dresselhaus. Thank you.
It may seem like an oxymoron, but the word nano is big and getting bigger. It has become part of our lexicon. We carry nanopods. We lather our skin with nano face creams and nano sunscreens. We clean our teeth with nano whitening toothpaste. We use nano wipes on our cars. We coat concrete as well as refrigerators and vacuum cleaner parts with nano sealants. In India, nano is the name of a car. In China, it is the name of a tea. According to a study, the number of products with the word nano in the label has since the mid-200s doubled every 18 months. Well, some of these products merely take advantage of a marketable term. Most, in fact, do use nanomaterials. Nanotechnology has, since its first application in the early 2000s, transformed material science and quickly found uses not only in the marketplace, but throughout the fields of chemistry, physics, and even biology. And as it seeped into the marketplace, it became a widespread commercial success with applications in nearly all sectors of manufacturing, pharmaceuticals, and electronics. Despite the ubiquity of the term in our daily lives, many are not aware of what nano really means and why it has become the source of so much innovation. The Greek word nanos, which actually means dwarf, has come to refer to the very, very small. 1 nanometer is a billionth of a meter, 10 to the minus 9. In physical terms, it is about the size of 3 or 4 atoms placed side by side. Nanoproducts notwithstanding, a nanometer is a measurement relevant to the quantum world, where objects have unusual properties and behave in strange ways. Colors, hardness, electrical conductivity, and other material properties change as scale changes. For example, bulk gold is inert. At nanoscales, however, gold atoms can act as catalysts. In fact, it is possible to tailor properties of gold and other materials simply by adjusting the size and orientation of their particles. We owe the realization that properties change as scale changes to many scientists, but our guest tonight, Dr. Mildred Dresselhaus, was one of the first. She laid much of the foundation for our understanding of how reduced scale influences the fundamental properties of materials. She pioneered the use of Raman spectroscopy as a tool to study the electronic properties of materials, especially carbon, on the atomic level. Dr. Dresselhaus, as we've heard earlier, has been described as the queen of carbon as a result of her early studies of graphite, the dark flaky carbon found in pencils. She then went on to study other carbon forms, including fullerenes, graphene, and carbon nanotubes, structures whose existence she contemplated years before their discovery. Along the way, she invented several techniques for studying individual layers of carbon atoms. She has also made and continues to make pioneering contributions to the study of thermoelectricity, a field she invigorated over 20 years ago with a seminal paper. Professor Dresselhaus, or Millie as she is known to most of us, is an institute professor and emeritus professor of physics and electrical engineering at MIT. She graduated from Hunter College in New York City and then spent a year at the Cavendish Laboratory at Cambridge University on a Fulbright fellowship. She went on to earn a master's degree from Radcliffe and a PhD from the University of Chicago. She studied superconductivity as a postdoctoral fellow at Cornell and then switched her focus to magneto-optics when she moved to MIT's Lincoln Laboratory. In 1968, she became the first female tenured professor at MIT's Department of Electrical Engineering and Computer Science. In addition to her research and teaching activities, Dr. Dresselhaus is a tireless promoter of opportunities for women in science and engineering. And in this role, she was appointed the Abby Rockefeller Mosé Chair in MIT in 1973. In 2000, she served as the director of the Department of Energy's Office of Science. And from 2003 until 2008, she was chair of the governing board of the American Institute of Physics. She also served as president of the American Physical Society, where I first encountered her, president of the American Association for the Advancement of Science, and treasurer of the National Academy of Sciences. Millie is a member of the National Academies of both Science and Engineering, a member also of the American Philosophical Society, and a fellow of the American Academy of Arts and Sciences. She holds over 20 honorary degrees and has received numerous awards, including the National Medal of Science, the Heinz Award, the Oersted Medal, the Nicholson Medal, the Vannevar Bush Award, the Weizmann Institute Millennial Lifetime Achievement Award, the Enrico Fermi Award, and most recently, and the reason she is here tonight, the 2012 Kavli Prize in Nanoscience. She is the first Kavli Prize recipient to be awarded a prize individually and not as a member of a team. This is a testament not only to her importance in the field, but to the esteem with which her colleagues hold her. As we've heard, the Kavli Prizes are bestowed every 2 years in the fields of astrophysics, nanoscience, and neuroscience. Each carries a cash award of $1 million. And true to form, Dr. Dresselhaus used her award money to set up the Mildred S. Dresselhaus Fund to support women and junior faculty at MIT. The Kavli Prizes are presented in Oslo, as we've heard, through cooperation with the Norwegian Academy of Science and Letters, the Norwegian Ministry of Education and Research, and the Kavli Foundation. We at the Carnegie Institution have very much enjoyed our relationship with these entities over the years, and we are extremely pleased that we were able to host Dr. Mildred S. Dresselhaus in her delivery of the Kavli Laureate Lecture. Please join me in giving Professor Mildred Dresselhaus a warm welcome.
Thank you so much for that wonderful introduction. I am still excited about nanoscience. I've been doing it for a long time, and I do hope at the end of my talk you will be excited about science at least, more excited than you were before, and nanoscience in particular. So I'm going to be talking to you about nanoscience as it pertains to nanocarbons. I like that subject because with carbon, you can make about the smallest nanostructures and study them in great detail. So it becomes a wonderful instrument for studying the nano world. So let me get going. What is nanoscience anyway? It's clear from this picture here that we have a scale, and here we're going up, we go up beyond 1 centimeter, which is the top of the scale. We have another 27 orders of magnitude when we're doing astronomy at the limits of what's known about the universe. But going down, we don't really have that many orders of magnitude. We go down here, we get down to 1 nanometer. There's an arrow here. That's at 100. So that we call the beginning of the nano world, 100 nanometers. So that's many orders of magnitude coming down. So 9 orders of magnitude makes a nanometer. And when we're down to 1 nanometer, we're at the size, here's 1 nanometer, and that's the size of the nanotubes. And most of my talk is going to be about objects that have diameters of 1 nanometer. And at that kind of diameter, you have about 10 atoms, only 10 atoms around the diameter. So we're getting pretty small. And the amazing thing about what I'm going to tell you, maybe that's a take-home message, is that we can actually study these little things at the individual level and tell you lots of things about them using light. And the wavelength of light is 3 orders of magnitude, meaning 1,000 times bigger. So that's kind of amazing, and that's what I'm going to be talking about today. So I hope you're impressed that science can do things that you don't really expect. So what's down there at the nano world? So we have DNA, and that's 2.5 nanometers. It's sort of larger. DNA is larger by quite a bit from the things I'm going to tell you about today. The quantum corral that was discussed by a previous Kavli Prize winner, oh, that's much larger too. That's a factor of 10 larger. So we're really getting to very, very small things. So that's what I want to talk about today. And as you heard in the introductions, the nano world is different because you take a material that's macro, ordinary size. That means you could see it with a microscope or something like that. That's ordinary size to us. The properties of materials are very different at that scale. And what I'm going to be talking to you about today is some of these differences that don't occur at even scales of 100 times bigger, which is kind of well below the limits of microscopes. But with the microscopes that we can make today, transmission electron microscopes, so these are not the ordinary microscopes that you have around, And they're not normally available. They take a very big laboratory to put one of these instruments down, so it's like almost like an accelerator, a mini accelerator. And those kinds of instruments can look at this world, at the structure, and we look at the spectra. So it's related, but we do it with ordinary instruments, just with light. Okay, that's what I'm going to talk about. And at the nanoscale, materials have different properties, and that's my focus. So I started in this business of studying carbon, which is the subject of today. I work on many other subjects, but carbon is a system that can be made very, very tiny, and it's just one kind of atom. So it's not only tiny, but it's relatively simple. And therefore, we can learn many more things than we can in complex objects. Science moves forward, and probably in 10 years, people are going to be studying phenomena at this level that are much more complex than we're studying today. But it's important to lay the basis of those studies on a firm foundation. And that's really where I am today. So, okay, I started with the carbon system because I thought that one we can get to small sizes and it's relatively simple. That's why I'm there. I started back carbon in 1960, and I started working in that after working in superconductivity for the 10 years before that time, because when I got my first independent job after finishing graduate school and a postdoc, I was told that I should work on something that's different, something that's interesting, and something that you don't know anything about, and nobody else does. So, well, the carbon field at that time had approximately 0 to 1 papers a year, and when I started working in the field, there were 3 papers per year. So that's what I'm trying to show in this picture. The publications and interest was sort of 0. And I worked this the first, I think, 10, 15 years. Nobody was interested in what I was doing, pretty much. But I was interested in it. And that's really important for young people. If you find something that's interesting, go for it. And sometimes it works and sometimes it doesn't, as the Kavli Foundation motto is. But more often than not, if you fool around with it enough, you can often make it work at least at some level. This worked more than at some level, and that's what I'm going to tell you today. So I'm going to go through this sort of historically because it gives you a picture of how you go from sort of nothing to something that lots of people are interested in, because you see this phenomenal growth that has occurred over the last 50 years. And it's still moving forward at a rapid rate. The European Union has just put in €1 billion into this project of nanocarbons. And it's a 10-year period that they've invested that much money, but that's a lot of money in just one thing, graphene. So somebody thinks it's interesting nowadays. All right, so where does it all start? So I got interested in this thing because it was different from anything that I had ever studied before or I knew about. And that is that the motion of electrons in this material, so that's the electronic properties of the material, which governs optical properties and many other things that you can do with the material, was totally different from anything else. And so to be a little bit technical, normally, you know that E equals mc squared, you heard about that. So there's a quadratic relation between energy and momentum. And that's the usual thing that happens for materials as well, except that the mass is not the mass of light, but it's mass of it's an effective mass. It has to do with the motion of an electron in the material. But anyhow, for this case, we have this linear relation, not quadratic relation, but any linear relation. And that means, it gives you the idea that carbon is different from everything else. And that's why I was attracted to work in it. Okay, so that's attraction. 10 years later, after studying 10 years of electronic structure and the lattice vibrations and all kinds of things about graphite, which were not known in the 1960s, I decided, after giving a talk actually at Bell Telephone Laboratories, they were the ones that really pushed me into moving into the nano world. And they suggested that I work on intercalation compounds. I gave a talk there, and somebody asked me a question that raised this. That's exactly what happened. And so what is an intercalation compound? What you can see here is that the intercalation compounds has a single layer. So we can make this carbon, this graphene system into single layers that we could separate with something, either ions or molecules. So I spent almost 20 years studying this, among other things. This wasn't the only thing I did during that period. But what I was studying is what happens, so you start with 1 layer, 2 layers, 3 layers, and that's called a staging. You can make compounds that have that periodic structure showing here, where the carbon could be just 1 layer, 2 layers, 3 layers, etc. And the whole point about this is the behavior of the carbon in that kind of form was totally different from what it was in the bulk form. And, okay, something missing here. So now I'm moving to the 80s quickly. The beginning of the 80s started, and I was interested in clusters. And so I said to myself, if we take light and we have a beam of light with enough energy, it may take some atoms from a surface. And I expected if I take 2 carbon atoms, 3 carbon atoms, I was expecting little tiny amounts of carbon to come out. But what happened was every day I was working in the lab, my clothes got very dirty. And I came home with, well, if I had a white blouse or any light color, it was just covered with soot. So I knew something bad was happening. So we did an experiment to figure out how much energy was required to take off carbon atoms, how much would be removed. And so I could figure the energetics going in and the size of the clusters. And it turned out that I was liberating something like 100 atoms at once. They came out in really big chunks. I had never thought about this, so I went to visit laboratory, Exxon laboratory. In those days, so now we're at 1984, in those days, the industrial labs were really doing great research, and the best place to study clusters was to go visit Bell Labs. This was actually not Bell Labs, but Exxon for this particular one. The last one was Bell Labs. This one was Exxon Labs, but industrial labs. And they had gotten up to C15. There's a peak at 15, you'll notice. And they had gotten up to that point, and they had stopped. They were interested in the clusters, studying the clusters, but they thought that was the end of the road. And I told them that was 1 order of magnitude, a factor of 10, less than what I was seeing. So I told them, please go to higher, larger clusters and see if you could make them. So they put a little more energy into their beams, and they made larger clusters, and they got this spectrum that's shown over here. And you could see that there's a bunch of peaks here. They're all separated by 1. And then is a valley of death. There's nothing happening in here. And then all of a sudden it goes again. There's another bunch, and they're are some peaks, C60 you'll see and C70. So that was very suggestive, but they didn't do anything about it. And Professor Smalley, Rick Smalley at Rice University, saw the same spectrum, and he got very excited about the C60 peak, and he said, we should investigate that more. And that was the discovery of the fullerenes. And here's the fullerenes. And this is one of our books on it, my group, but I'm sure he had a book of his own. And that's how I got into it, because I got into studying the spectra of that. In the 1980s, at the same time concurrently with this, I was studying carbon fibers. I got into carbon fibers through international collaboration, and the discussions that we had before introducing me. We talked about the world scene of science. Norway is a European country. There's a lot going on in Asia. So the whole world is doing science. And the people that were really ahead in the carbon field at that time were in Japan. And I had a collaborator who I met in 1980, a younger person, younger than myself at that time, because he was just starting his career. And he had presented a paper on carbon fibers. And I got very excited about hearing this paper, because I saw a carbon fiber is long and thin, and I thought this would be the greatest sample to do intercalation physics. So we started a collaboration, me and this Japanese scientist, and we were going to do intercalation physics, which we did, of course, for 10 years, and we're still collaborating since 1980, so that's a long time. Anyhow, I became well known in the field of fibers, and in 1990, there was a conference here in Washington. It was a very small conference. There were maybe 20, 25 people, not very many. And Professor Smalley, whom I mentioned about the fullerenes, was invited to speak about C60, and I was invited to speak about the carbon fibers. And somebody in the audience asked the two of us at the end of the conference what was the connection between carbon fibers, which have many, many, many atoms, and C60, which has only C60 carbon atoms. So what's the connection? And so we came up with this. You take C60 and you stretch it out. You can make C70. That was already known in the spectrum I just showed. C80 was not known, but just keep going. And then eventually, maybe you can make a fiber. The fiber would be just one atom thick. Well, that sounded like a little bit of a crazy idea to both of us. But what happened is that both of us decided to think about this in the future and maybe even do some work on it. Smalley was an experimentalist, and so he was the guy that actually made materials, and he eventually made a single-wall carbon nanotube, just about the same time that some other people did. So he was right in the original making. And in our group, we did something else. We said, suppose you could make such a thing, what would its properties be? Would it be worth putting a lot of effort into that line of research? So our paper came out just about the same time as the people that tried to make multi-wall nanotubes. No single wall yet, but our paper was on single wall, and then people got excited about making single wall nanotubes, and within a half a year we had all of that information. So what was our excitement? Why were we excited about that? So if you take a sheet of graphene, so this is what a single layer of carbon atoms, you could see all the hexagons, so that's one atom thick layer. Nobody had made that at the same time, but we had been thinking about this for years. Suppose you roll that up, you get something like this, and it has very few atoms, maybe 10. That would make a nanotube that it was 1 nanometer in diameter. That's the sort of nanotubes that we work with nowadays. So suppose you could make that. Would that be interesting, and what would its properties be? So we did a simple calculation, and that was published in this paper. At that time, we had 2 Japanese visitors that arrived at the beginning of the year 1991. And they were looking around for a project to do. They had a fellowship from the Japanese government, and they were looking for some research group to give them some ideas about what kind of calculation might be interesting. And somehow they stumbled on me, and I suggested doing this problem, that we work on this thing together. And so within the year, we published this paper in 1992, and it predicted that depending on how you rolled up the tubes, so here is the linear E versus K that I talked about, that you would have for a fuel layer system. And then we're going to make these cutting lines. So if you have 10 atoms, you have 10 cutting lines. You take the cylinder, and you would only have allowed states in 10 ways. So you would have these 10 cutting lines. And if a cutting line happened to go through this apex connecting the conduction band and the valence band, so the valence band would always be filled, and the conduction band would always be empty if it was graphene. So the idea is that if you had these things joining each other, a common value of energy and momentum, then you could have a metallic state. Otherwise, they would be semiconducting. So that was the basis, the physics behind this whole thing. And the density of states would have these peaks because we have a linear system. And the linear systems, the energy momentum relation is spiked. And that allows you to do very strong resonance experiments from one state with a high, at the valence band, that has a very high density of states, like one of these, to a corresponding state at the conduction band that's empty. And that excitation could be done with light. So that was our experiment, to do that kind of study. So that study was done. Here's Raman spectra. And what we found here is that the spectral analysis proved that we had a resonance state, so that was, it confirmed the idea that going from valence to conduction band would be resonant, and we would get 3 orders of magnitude, that's a factor of 1,000 enhancement of the signal. And because of that, it was possible to see very few carbon nanotubes, and in fact, a single nanotube could be seen. So after we got this result with this very high density of states, and we got this particular feature, that's a spectral feature that has to do with the carbon atom vibrating in the radial direction in and out in a breathing mode. And when that happens, since the diameter changed, we would have a measure of the diameter itself because the diameter was going from equilibrium in and out. So that gave us the diameter of the tubes that we could measure. So that was the beginning of single nanotube, nanotube spectroscopy. And because the signal was so strong, we could see it on an individual nanotube. And the spectrum was different. So here are individual nanotubes. And this is done in a collaboration with Charlie Lieber at Harvard University. So he was a chemist, and he made for us, or one of his students made for us, these nanotubes in very, very sparse arrays. So we could separate individual nanotubes in the microscope and then do spectroscopy on just individual tubes. And with that, we were able to get the spectrum of a single metallic tube and a single semiconducting tube, in fact, to do many, hundreds of them. And so that's the beginning of single nanotube spectroscopy. That's the first paper on that. And that turned out to open up the field because we could study all of these different tubes, because depending on the diameter and how the hexagons were arranged along the axis, it was different for every single possible orientation that you could have. So there were a few hundred of them that different chiralities, as we call it, that you could measure. So that kept us busy for quite a few years, and it was exciting times. But as soon as we published this paper, we got a big increase in interest. Lots of people started doing spectroscopy and many other measurements on these tubes, because new ways were found to find the chirality. If you find something in science one way, then people do experiments and they find it another way, and some are much simpler than what we had. But this was pretty simple, so many people remained using spectroscopy. So what are we doing now? So we moved from working on just single nanotubes, and now we work on double nanotubes. So here's double nanotubes. So we do the spectra. So there are four possible. You have metallic and semiconducting. You can have inside or outside. So you have four different combinations. And well, this machine moved by itself. And so it's showing me that you can make double wall. This is double wall, and this is triple wall. So we study 1, 2, and 3. We don't do more than that because it gets too complicated and it's too time consuming. So we stop at 3, but you can do 4. 4 is possible. Beyond that, I think is crazy. It's too much work. But this gives you the idea that you could really build up your repertoire and understand the interaction with tubes. So you take a particular tube, and it could be the inside tube, all by itself, single wall nanotube. Then you take the same tube and put it in 2 tubes. And it changes because it has an interaction, and it's different if the outside tube is metallic or semiconducting. So you can study all of these things, and that's a kind of way to study what happens with these materials that are very different from what they would be in the bulk. So that's a little bit about nanotubes. And so here's triple wall nanotubes. And this is some work I'm doing with a visiting student who, he came and spent a year with us at MIT as a visiting student, but his degree is in Germany. And so he's finishing up his degree, and then he comes back, and we're in touch. But we keep writing papers together. So that's an activity of my group, and it's a part of the way we do international science. It's very good for the student that comes, and it's very good for the students that are in my group at MIT, because we have several visitors at once from different countries, and they talk to each other, and they learn lots of things, not only science, but also culture and how science is done in different places. And they make relations that last for their whole lives. I think that's another thing that I would think that the Kavli Foundation would be very happy, and also the Carnegie Foundation is part of interest in that sort of thing. Okay, so I'm not going to say a whole lot about graphene. Graphene has been studied by lots of people in recent times as part of this big explosion of interest. And they do similar things that what I was talking about, but they're actually much simpler, because you don't have to worry about chirality, you don't have to worry about curvature of nanotubes and all of this kind of thing. So my feeling about graphene is that's the material that should have been discovered first, but it wasn't. It could have been, because to make many of the experiments that were done from 1960 on, at least in my lab and many other places, could have been done on graphene. The simple way that they prepared graphene, as I'm going to say in a moment, this graphene was found and isolated in 1961, and the paper came out in 1962 in Germany. Very few people, including this research group, followed up on it. It was not recognized as being very important. A single-layer graphene has linear E versus K, and you really observe the linear E versus K. And bilayer has quadratic. Aside from that, when you do dispersion relations, look at the relation between energy and momentum, throughout all the different possible values of energy momentum, it looks very, very similar. But since all the action is taking place in these materials, taking place right here for a very small part of this momentum space, the properties of single-layer graphene and bilayer graphene are really quite different. And that's what is occupying scientists right now. And I would imagine that you have other people coming to speak on that, because this is a very popular area. And if you don't, this is a good topic, people will be interested in it. So here's single layer with the linear E versus K, and bilayer on your right with the quadratic form. These materials are made by what we call the Scotch tape method. And so you see Scotch tape there. And you take, say, graphite or something like that, and you start peeling. And you peel and keep peeling until you get one layer. It looks sort of messy in the beginning, but you just keep going with that until you get single layers. And so it looks something like this. And eventually you get a region where you see just a single layer. It's labeled here monolayer. And with a microscope, and this is seen with pretty much an ordinary microscope, it's not a very special one, it's possible with appropriate substrates to observe this. And this is the work of Geim and Novelties, and they have the Nobel Prize for this. This is the beginning of the work, but what they did is not only observe this material, but they took it very far away in a very short time. So graphene has amazing properties, and it's very thin, single layer, just like the single wall nanotubes. That's not so different. It has a zero band gap, as I mentioned, linear E versus K. It has a high mobility. The samples that were made for the first few years were no different than the nanotubes that we were using. But because you have no defects, you don't have the curvature problems, you can have a much higher mobility. And I believe that the record that was observed is about 1 million under certain optimal circumstances and low temperatures. The thermal conductivity is very high, but so is it for graphite and for nanotubes. So that part is not so different, and that it's able to carry high current densities, perhaps a little bit higher than nanotubes, but really nanotubes are very good in doing all of these kinds of applications. I'm going to end my talk with graphene ribbons, because this is an area that I have been interested in and we've been working on for a bit. And it brings me in closer to part of my Kavli Prize, which was about thermal energy and its uses and how we how it modifies materials and allows us to do science that otherwise would be difficult to do. So that's why I'm telling you about this area of research in our group. We started this work about 15 years ago, a long time ago in 1996. And so we got interested in the fact that you can make a graphene sheet. So here is zigzag. You can see the edge zigzag. And this one is armchair. So there were hexagons, but the way you cut the hexagons gives you different edges. And so this field was opened for us by a theoretical paper. Suppose you can make this, would it be interesting? You ask the same question. So this is a Kavli kind of question. Suppose, is it interesting? So what the calculation showed is that if we had the zigzag edges, though it looks just like zigzag, independent of what the diameter was, the density of states would be very high right at the Fermi level. So these kinds of ribbons would have very special properties. In fact, they would have very interesting magnetic properties. So that came out of this early work. But if they had the armchair edge, we could have possibly a zero gap, but we could also have real band gaps depending on the width of the ribbon. So that was the prediction. It took a few years to be able to make a ribbon that was good enough to verify this prediction, but the theory turned out to be correct. Well, theory was developed in a few years much better by the people that did more detailed calculation. This is sort of the simplest calculation you could do. The addition of spin-orbit interaction showed that the degeneracy was not perfect, that there was a small band gap, and showed many other things. So what science always does is with time, it gets more sophisticated, and then you understand it better. But this is the first approximation, and this opened, at least for us, the field of graphene ribbons. And so we've been doing microscopy and Raman spectroscopy together on the same samples. So we get structure and we get also properties. So, and you can do transport as well. And this is some early work. But I'm now going to go fast forward with this. And here is a ribbon in the corner. You see here, it's a kind of folded up ribbon. And if you cut that into little tiny pieces, you get a flat ribbon. And then we can measure that flat ribbon. And what it showed is that if we put just running current, so a plot of current and voltage, this is something anybody could do in a lab because the voltages are very small. So this is not very difficult for people to repeat. So it was repeated very soon after we published the work. And if you go up to a certain point, this IV curve gets nonlinear. And at some voltage, the whole thing takes off. And we go from a material that looks kind of very messy to something that really shows large area facets. I'm going to show you in more detail when you have on a higher resolution. So here is the ribbon that we have. This is one version, and this is the higher resolution version. And this is done with a simple microscope, a TEM, transmission electron microscope, but it's not an expensive one. It's not a fancy one. It's the student one that's in the student laboratory at MIT, so it's not very fancy. And you could see by eye the zigzag and armchair edges. So that was kind of interesting. And gave us the idea that doing current flow and studying the energy transfer in nanocarbons would be interesting. So now I'm going to go back to early work. This is sort of the end of my talk. This is work of some collaborators of mine, but I'm not on this paper. This is just, I was talking to them about it. But we did similar work about the same time and also published. I think our paper came out a little bit later than this, but you see these two atoms over here, and I'm going to show you after a little bit of electron beam irradiation. We did the same experiment by putting a current, IV, but it's a similar thing, supplying energy so that you have heat transfer. That's the concept, and you can do it in different ways, and it makes 2 nanotubes coalesce to make 1. And that's another area that we're studying now, of taking taking a nanostructure, using thermal energy to change the nanostructure into something else. And just going back to this, we had observed this, but I didn't do anything with it. And then when the Kavli Prize came along, I said, gee, I didn't really deserve this, because some of the things that they said in the citation, I didn't really do very well, not to my satisfaction. So I said, well, I better go back and repeat some of our early work. And so now we're opening a new research area for ourselves and doing this kind of experiment, taking nanostructures and making new kinds of nanostructures. So I imagine this will keep me busy and interested for a few more years, but I can't tell you a whole lot about that. Another thing that I've been working on is, this is very popular now. We have graphene, that's a flat layer, but there are other kinds of materials that are flat layers. We know them from bulk studies. I was studying MOS2 for lubricants with Reshev Tene 20 years ago in bulk form, and I had some visiting students at MIT, so we had a serious international collaboration of sending students back and forth from the two sides. And the bismuth telluride, I have a collaboration that's similar with exchange students going back and forth with people in Singapore. So this work that we do in science is so international, and we benefit a lot from each other's discussions because everybody does it a little bit differently. So when they come visit, we learn many things from them. So that's what I'm going to end my talk with. You saw this picture before, I guess. And I would like to thank the Kavli Foundation, not only for what they did to me and getting me excited about starting a new field for myself, but I think that going to lectures that are somewhat out of your area is a very good way of finding out what the rest of the world is thinking. And maybe if 1% of them stimulate some new research direction for you, or something that changes your life in some way, it's a very good use of your time. So that's why I go to attend myself. I always find time to, I probably go to some seminar every day. And maybe half of them I don't really know too much about, but I learn new things, and sometimes they're game-changing. So anyway, that's the way I operate. I don't know if it's the best way, but it keeps me happy. And thank you for listening to me, and I'm happy to take questions.
That was terrific. Thank you very much.
We do have time for a few questions, and there are microphones in the middle of each aisle, and I'll invite anybody who has a question for Millie to come to a microphone.
What sort of interaction is there between the scientists doing very basic research on the properties of nanomaterials and the folks trying to make it into products that we can go out and buy?
Okay, that's an excellent question, and I'm glad you asked it. So the interest is our relations with industry. So the university I've been associated with for 50 years is MIT. We have something that's called Industrial Liaison Program. And there's a great incentive from that program for faculty to interact with industry. So what happens is we get a tiny little bit of money when we have a discussion. It's not enough to send a student to a conference or anything like that, but if you have 2 or 3 of those interactions, then that's the reward. But I don't really do it for that reason. For me, interacting with industry, I get ideas from them. So that's my incentive. So we have contacts with industry. We have different seminars, like next week on the 1st of November, that's approximately a week from now, we have a meeting that will be 2/3 people from industry who are invited on the subject of nanocarbons. And 1/3 of the people will be researchers, mostly from MIT, and they'll be talking about what they're doing, and maybe we'll have a couple of speakers from industry also talking at this. But we have a good bit of time during the day for sitting together and talking to each other. So that's the way these relations start, and we learn different things from each other, and sometimes some products come out, but that takes a while, and for a real product to come out, that takes 15 years, right? And so it's not immediate, but it's happened to me and my colleagues that things do happen in the real world.
We have another question.
So people often mention that you are the woman pioneer scientist. What has been the most challenging situations for you during past 56 years, and how did you overcome those issues?
Oh, that's an interesting question. So over the period that I've been engaged in my own research, so I was an independent researcher. When I started, we never saw a woman at all in doing what I was doing. So it was kind of lonely that way, but I liked what I was doing, and I thought all these other women were missing something by not doing what I was doing. So at first we had essentially no women students in the class. It was very, very small numbers. We had women students at MIT, but they weren't studying physics, and they weren't studying most of the engineering kind of courses that they would take my course. But with time, I got more and more and more. And I think that I got more than students because they wanted to see me doing something. So I think I attracted some. And I've had more female students percentage-wise than men faculty in my departments. So I still have many more men students than female students because that's the way our fields are at the moment. But the change with time is enormous, and the opportunities for women have increased even more enormously. And it used to be a handicap being a female. Now it's not a handicap in being employed. When you get the job, combining a career and a family is not trivial. And so I try to help people with that. Just saying there are many ways to do it, and we gather some representative females that have, at our place we have lots of them, examples on the faculty at the moment, because it's grown so much, and we try to help each other.
Another question? A very young questioner.
How do you make graphene?
Well, for you, if you want to make graphene, the Scotch tape method is your method, because every child can just take a piece of graphite. You walk in the woods in the right place, you can find that on the ground. Or you can maybe buy some. It's not very expensive in the toy store. And peel some, and then look at it under a microscope. That could be the first. If you have a microscope in your school, simple microscope could be enough. Want to try that?
You can go downstairs and do that.
So,
Toby.
speaking out of my field, thank you very much. The transition or the looking at whether something is metallic or a semiconductor, is that controllable? And does that have anything to do with the zigzag and the chair?
There's a relationship, of course, between the structure and the properties, okay? But when you first see your nanotube, you don't know whether it's metallic or semiconducting. There are many ways to find out. The easiest way is to put two leads on it and run current. So
Well, is it possibly the diameter of the nanotube, and that's why
well,
may end up with
at a given diameter, roughly speaking, in a range between this and that, there'll be semiconducting and metallic. Right? But if you have a given diameter, you could have either kind. When you get to very, very smallest kind of diameters, then they're one thing or another at that diameter. Mm-hmm. But if a given nanotube has a given chirality and it's either semiconductor or metallic, it's not both at the same time.
Thank you.
Our final question.
This is actually on a similar note. It's about a sheet of graphene. I couldn't help but notice on the slide that one edge of the sheet had a zigzag side or a zigzag edge, and the adjacent edge had an armchair. So I was wondering if the metallic or semiconducting property is dependent on the direction of the current. How does that work?
Okay, so when you have a graphene ribbon, then, as I explained, you could, if you have mixed edges, you won't have mixed edges on a given orientation. So there'd be either one or the other. Because if you make parallel cuts, there'll be the same kind of structure.
Okay.
Okay? If you look at the way the hexagons go.
Okay, thank you.
Well, Millie has been an inspiration to, I know, generations of students. And I can understand why after her presentation this evening. Please join me in thanking her for joining us.
I enjoyed coming.
Yeah, it's wonderful. It's wonderful. Great to see you. Thank you all for joining us. We're now adjourned.
Adjourned.